Hello, everybody, and welcome to the Unit 5, Work, Energy, and Power. All right. We're going to start right into Section 1, which is titled Work. And I know everybody, if you're thinking about that word work, I'm sure everybody thinks they know what work means. Well, as always in physics, work doesn't mean what it means everywhere else. So, what does work mean for us? All right. Work is what we call the process by which energy is transferred or converted into a different form. All right, so anytime energy is transferred or converted. All right, energy we're going to define as the capacity or the potential to do work. And I know this seems a little bit circular um, as far as the definition goes, but we'll start to see really what the difference between these two words are. So first, forces are the things that actually do work, all right? So when a force acts on an object, it has the potential to do work on that object, all right? So the forces are the way that the energy is actually being transferred to an object or away from an object or being converted from one type of energy to a different type of energy. And as we'll see in section 3, we'll see at least two different types of energy that we'll be using in this unit. All right. So when we measure the work that's actually being done, we are measuring the amount of energy that is being transferred or converted by a force. All right. So work is the process. It's the measurement of how much energy is actually being transferred. Energy is the thing that's actually being transferred. So energy itself is the ability or the capacity to get something done. All right. So we often say when work is done, energy is the currency. All right, so we move on next to just what the equation is for work. So we see in this equation the capital W. You could probably all take a guess that that's going to be work. All right, F here is still going to be a force. Okay, D is going to be distance. And we have this cosine theta thing, and we're going to talk about that in a second. As far as units go, we're going to bring back some units from your chemistry class. And so work, we're measuring energy, all right, or the energy that's being transferred or converted into a different type. And we know that the units for energy are joules, so that's what this is going to be. So work is going to be measured in joules. All right. And that's going to be abbreviated with a capital J. We're already familiar with force. Force is measured in newtons, right? Distance is going to be measured in meters, and theta is again going to be in degrees. All right. So I want to point some things out about this equation about whether or not work is actually going to be done. So first, let's think about whether or not distance is 0. All right. So in this equation, if we replace d with 0 meters, then immediately what we're going to see is that the entire right side of the equation becomes 0, and so the total work that's being done here is 0. In other words, if something doesn't move, all right, then no work is actually going to be done, or no energy is going to be transferred or converted. So objects have to move for work to be done. They have to go from one place to another. We can also look at force, and we can say, all right, if the force is 0 newtons, what happens? Then no work is done. So here's the other thing. If you don't have a force, then there's nothing that's actually going to transfer the energy or convert it into a different type. So you have to have a force, and the object has to move a specific distance for work to be done. All right. So what about the whole theta thing? All right. Theta is the angle that goes between the direction of the displacement and the force. In the picture down below here, our object is moving from the left to the right. So it's actually moving to the right, and that's the direction of the displacement. All right? So that is going to be where we point our positive x-axis. We're going to see how this is going to change when we do some of our examples. All right? So theta helps us find the component of the force that is actually parallel to the motion. That's where the cosine theta actually comes into play. So the cosine is going to help us find the parallel part. And that's because only the parallel component actually does any work. And we're going to see some examples of how that plays out as well. So let's start with some examples. All right. In these three examples, we're going to use the same force every time, or the same magnitude of the force, and it's going to be 10 newtons. And then we're going to have every time, we're going to have the distance that this thing travels be 10 meters, and it's going to be off to the right by 10 meters. And what we're going to look at is how the angle theta actually changes the amount of work that the force is doing. So let me just review that for a second. So remember, forces do work. Work is transferring energy. So each of these three forces is actually going to transfer or convert a different amount of energy, and that's because of the direction that the force is actually going. So when we talk about direction, we're talking about the standard angle between the displacement and the force. So in our first example right up here at the top, all right, our force is pointed in the same direction as our positive x-axis. And if they're pointed in the same direction, then that must mean that the standard angle between the two is 0 degrees. All right? In the second example, we see that the force is pointed off to the left, but the object is actually moving off to the right. So we start at the direction of our displacement, and we go all the way around, and we see that the standard angle for this force is 180 degrees. And in our third example, we have the force, and it's actually going up at an angle there. So we're still moving off to the right, but our force is not directed to the right. It's at 45 degrees above that horizontal line. All right, so in this case, my standard angle ends up being 45 degrees. So if everything else is the same about these three, all right, so if every one of them has a force of 10 newtons, a distance traveled of 10 meters, all right, so force, 10 newtons, a distance traveled, 10 meters, a force, 10 newtons, a distance traveled, 10 meters, all right. Then when we go to calculate the work that's done by each of these forces, we would expect it to be the same because it's 10 newtons, 10 meters. But that angle has an effect, all right? So let's look at how that angle affects it. So work is equal to FD cosine theta, all right? And so in this case, we're going to use our force of 10 newtons, our distance of 10 meters, and the cosine of 0 degrees. Well, the cosine of 0 is going to be 1. So we have 1 times 10 times 10, which gives us a positive 100 joules. So remember, work measures the amount of energy that's being transferred by the force. In this case, we have 100 joules of energy that's being transferred by the force. All right. In the second example, we have the same equation, FD cosine theta. All right. A force of 10 newtons, a distance of 10 meters. Should be the same, except the cosine of 180 degrees gives us a little different answer. Cosine of 180 degrees actually gives us a negative 1. So we have negative 1 times 10 times 10, which gives us the total work done by this force of negative 100 joules. Now there is a big difference between negative 100 joules and positive 100 joules, and I'll bring that up in just a moment. All right. In our final example, again, FD cosine theta. All right. We have a force of 10 newtons. We have a distance of 10 meters. We have the cosine of our angle, which is 45 degrees. And in this case, we don't get 100. We don't get negative 100. What do we get? In this case, we're going to get 70.71 joules. All right. It's not even the same number, all right? So the first two, we get hundreds, but then for this last one, we get 70. So what's really going on here? All right, it's only the force that's parallel to the direction that we're moving that's actually going to do any work, that's actually going to transfer any energy. So in the first one, we see that all that force is pointed in the same direction, so we're going to add 100 joules worth of energy. In the second one, the force is actually working against us. It's in the opposite direction of what we're moving, and so it's going to actually do negative 100 joules worth of work, which means we're actually going to take 100 joules worth of energy away from this object. In the last one, it's only this force right here that's actually parallel. So just the x component of that force that's actually doing any work. So in this case, only the x component of that force is going to actually do 70.71 joules worth of work. All right, and so we're going to actually increase our energy by 70.71 joules. So that brings up the discussion about the positives and the negatives. All right, positive work means that energy is actually going to be added by the force. All right, forces that are pointing in the same direction of the motion are transferring energy to the object. All right, so when they're pointed in the same direction that you're moving, you're transferring energy to the object. When you're doing negative work, you're actually taking energy away in this situation. So you're removing energy from the object. Forces that point in the opposite direction of what you're moving are going to be taking energy away from the object. All right? So if I'm moving to the right and something is pushing off to the left, it's taking energy away from me. That's negative work. Whereas if I'm moving off to the right and something is pushing me to the right, then it's going to add energy to me. All right? And I get positive work that's being done. Now, friction is one of these forces. It always points opposite the direction that you're moving. We have that in our notes from earlier, right? So by definition, friction is always taking energy away from the object. And so we see this in practical life when we look at an object that has friction acting on it, that we're going to either lose velocity or we're going to lose acceleration as a result of it. So losing energy, we can actually see that energy loss in the way that the object behaves. So in summation, all right, work does not have a direction. So positive and negative don't mean to the right and to the left for us. In fact, it really means that energy is either being gained or energy is being lost by the object. All right, so what about this example? So in this case, I have a 15 Newton force and it's pointed straight up, but I also have this object moving off to the right. Well, all right, we have a 15 Newton force. It travels a certain distance, 20 meters. We would expect to see that this force is doing work. But when we punch in all of our numbers, we find out that actually this doesn't do any work. 0 joules worth of work. So why is this, right? Well, mathematically, it comes from the cosine of 90 degrees, which is 0. And that makes the entire work 0. But why is that the case? Well, see, here's the thing. This force doesn't do any work because it's only the part that's parallel to your motion that does any work. So this 15 Newton force has no parallel component. There's nothing to the right and there's nothing to the left. It's all straight up and straight down. It's perpendicular to the motion. So that by saying that no work is done, what we're really saying is that this force does nothing to transfer energy to the object or convert energy in this situation. So even though 15 newtons worth of force is acting on this object, it's not at all helping to move this object from one place to the other. It's working perpendicular, and so it does no work. So we can say that forces that are perpendicular to the way that you're moving are never going to do any work. So perpendicular forces to the motion, they do not do work. It's 0 joules. And that's because cosine of 90 is going to be 0 degrees. All right. So in our next video, we're actually going to start into our examples, and we're going to look at this stuff a little bit closer, and then we'll also answer some conceptual questions at the end. So I'll see you in the next video.